All right, good afternoon, folks. I'm Doug Sibley. I'm a tech lead on the anti-spam threat research team with Cisco Talos. Today we're going to take a look at list bombing email attacks and kind of how we set up our telemetry pipelines to be able to quickly hunt for these kinds of things. This is the forward-looking statement. By attending this talk, you have agreed to look forward for the entirety of this talk. If we see you looking in other directions, we're going to double the price of your DBUs. So first, let's take a look at what an average day of email looks like for a user. So this is, in fact, my telemetry. What we're looking at here is email volume per minute across 24 hours. I would imagine most of you kind of have similar trends if we were to look at your data. The first thing we see through the entire period is a set of emails coming at regular intervals. These are some automated alerts coming from various Databricks jobs, queries I've running. From the density, you can kind of start to see that my main working hours are on the East Coast. The times you're seeing on this graph are UTC. My high water mark was 2 instances of getting 5 emails in 1 minute. The key takeaway here is, I'm a human, spoilers. I get some automated emails. I get emails from Jira. I get emails from other people. But I don't constantly send and receive emails. Nobody really does. Now, let's take a look at a different user's telemetry. So this is someone who's having, a very different day than you or I. This is the same view of a 24-hour time period, again, graphing emails per minute. Early in the day, we can see, maybe there's some spikes of emails up to 10 or 20 per minute. This seems high, but I would say it's not unheard of for some people who were very communication-centric in their work. What is unusual, and maybe you notice this on the graph, there's this very obvious prolonged spike later in the day. This is a period of about 1 hour where the user's getting dozens of emails per minute the entire time. The high water mark being a period where they're getting an email more than once per second. Imagine the constant notification alerts you'd see on your desktop, or getting a mobile alert for every email on your phone. This would be no fun. So what exactly is happening to this user? I've pulled some of the subject lines from this event storm. If we take a look at them, something pretty clear is happening. So first, they're getting emails about confirming subscriptions or registering accounts or signing up for newsletters. They're getting emails in multiple languages. This user might be a polyglot, but I'm betting they don't really conduct their normal business in multiple languages. I'm not showing you this data on this slide, but these emails are coming from sender addresses that have never emailed this user before, and some of these addresses have never emailed any of our users before. What is this user's name? Is it Ra Elvi Jix Quixis? Is it U Jax Tide Vol Sixted? We checked. This user is not an ancient Roman. They're a regular person. This is gibberish. So maybe you're seeing what the attacker did here. There's a huge variety of systems on the internet, which lets you sign up with an email address and download a white paper or register an account, all sorts of stuff. If you don't think that's true, please go down to the expo hall and get your badge scanned. You're going to be rolling in those emails. But why would an attacker do this? There's 2 reasons. One's just to be a nuisance. You need to watch the world burn. It's a denial of service almost. Something just intended to cause grief. The other thing is to drown in the noise, right? If I'm trying to compromise an account of yours and I trigger a password reset email or some security alert, are you really going to notice that email if you're getting an email every 2 seconds? Looking at this from the anti-spam perspective, a lot of the tools in the toolbox don't really fit. For account registration or marketing emails, the sender is actually doing the correct thing here. They're trying to confirm that the recipient wants to be signed up. The email itself is not malicious. The sender is acting in good faith. So detection systems which focus on bad email content or behavior, they're not in scope for this attack. So having introduced the attack, let's dive into how we tackle this from our telemetry, starting from before we even know this is a problem. For threat research, this is always the starting question of we have data, we clearly care about the data, but we don't know what the critical questions are going to be for our data yet. So this is a cut-down example of some of the fields we have in our telemetry. I'm omitting a lot of more specific technical subsystems and responses. Fortunately, in our architecture, we have our product emitting protobufs into Kafka, and these then get written out to a Delta table for us. Because they're protobufs, our table schema is defined in the protospec. All the messages we ingest will align to this schema, so this is much nicer than trying to wrangle JSON into a table with the moderate cost of we had to build a protospec ahead of time. The fields here are some of the things that most obviously we would be interested in searching through. Every event we process has an email ID. This is a UUID4. We obviously have a timestamp of when it was processed. Then we have the more email-specific attributes, things like the sender, the recipient, subject lines, IPs, URLs, attachments, these kinds of things. This data is a mock-up. Here we're seeing, maybe I'm emailing myself about my boat sinking, or maybe the email's like a metaphor, right? And this is some sort of like silly marketing. We don't really know because we don't see the content of the emails in this telemetry. We just get the metadata. So clearly we can write out a full table with our schema, but we also clearly have some fields which we want to search on. And so the question becomes like, which of these columns do we want to liquid cluster on? There's more than 4 that we care about, which is the single table limit. But also every column you add to the clustering spec, you're going to like notionally lose some of the specificity on the other columns. So we don't want to like just pack out our clusters if we don't think we're going to need it, because it's going to degrade the things we do care about. So to get around this limitation, we're actually going to tackle this with multiple tables. So first, we're going to set up a table with the full telemetry record, and we're going to cluster that just by the email ID and the message timestamp. And then additionally, we're going to set up several secondary tables. Each of these tables is intended to let us do optimized queries on that specific observable. So we'll cluster that table again by the message timestamp, but then we'll also cluster it on kind of like an optimized version of that observable based on what the data type is. So for example, when we're doing sender addresses, we could cluster on just the raw email address. But a question that's probably interesting is sometimes is like, what are all the various addresses that sent us something from this domain? So clustering on the reversed sender FQDN, this lets us answer that question very quickly while still supporting the kind of like fast lookup of single addresses, which is what we cared about. In these secondary tables, we're not going to store a full copy of the telemetry event. It's like just a handful of critical fields, a few things like our final message verdict or the data center this event was in. These fields are low cardinality, so they compress very well into the underlying parquet, and they're very cheap to include. So again, the starting point for our tables is actually not Kafka. Again, there's a separate production job, which is reading Kafka and writing the full telemetry record to a starting Delta table. For our jobs, we're going to be doing a streaming read from that Delta table, which means we don't have to like manage our Kafka secrets in this workflow, which is nice to not have to do. The goal of my workflow is to take every event and land it into the various tables. So a single record needs to go into our main telemetry table. Then we need to also extract and format the observables for the secondary tables and write them out. Now, the thing we really don't want to happen here is to lose events, right? When everything's operating normally, the upstream Delta table is landing new records every 60 seconds. So we want to get that data into our search tables as quickly as possible. The upstream table is partitioned by date and hour, so a simple design for this would be to just run an hourly query, which dumps the telemetry from the hour prior. But this introduces like a lag. You also need to defensively code this because if there's some sort of delay upstream, you can't really assume the prior hour will always be available right at the top of the hour. And kind of in these constraints, far and away, the easiest way to accomplish this, from my experience, is to just use stream processing. So with checkpoints, you can checkpoint on write, and it will handle restarting without a lot of problems. You can restart your jobs. All of the table inserts, they're fairly straightforward ETLs. So like we don't have to do super advanced transforms in a streaming context. And we're getting to land this data almost instantly from it being available upstream in our Delta table. So we get very fast search on top of this. The job's gonna have a sync for each of our tables. So we have the main telemetry table and kind of the specialist subtables. There's like over a half dozen. But the data's all coming from the same source. So we just have a single workflow, which is writing out to the tables to leverage Delta caching. So I have a bit of like banter with some of my colleagues who prefer PySpark. I prefer more SQL. When it comes to Databricks, at the end of the day, it actually doesn't matter. The real battle is going to be with the query planner. So it's like some things are easier in one paradigm versus the other. But in practice, you can just like switch between the two at any point with Spark SQL commands, or you can just go back to your PySpark native. So you don't really have to tie yourself to just one. This is an example of one of the table write ETLs. So it's a stream processing job, so it's easier to control the stream behavior using like read stream and write stream functions. But the actual data reformatting in the ETL, I first prototyped in SQL, which is why it's nice to just be able to swap the syntax on demand and not have to re-implement it. So we're going to start by creating a streaming data frame from our table source. We register it as a temporary view and then switch over to SQL to do all of the ETL. And then we can register the result of that as a temporary view and jump back into PySpark to actually do the final writing of the data frame. So this flow works well for me. Most of the time when I'm going to be writing out a table, it first started as like a set of exploratory SQL queries against something upstream. So I already worked through queries to get the format I want. To be able to lift and shift it without having to redo it is very nice. One quality of life piece is to like extract as much of your SQL ETL logic into standalone SQL functions as possible. In one of these SQL statements, you'll see me calling shared.funcs.email to reverse domain. So this is a string manipulation where we split an email address on the @ symbol, we split the FQDN on all the periods, we reverse those tokens, and then we rejoin it with periods. It's not hard, like we could write this every time, but maybe in one notebook you do it wrong and kind of everything breaks. So we can just encapsulate this using a SQL function, and it saves a lot of sanity. So like having built all these tables, what does it do for us? First, we have our main telemetry table. It has all of our data. And so this table is optimized for fast point lookups. In support, like the most common question you're going to be is, what do we know about event X? So being able to pull that event out very quickly, that's a must-have. Our secondary tables, they're going to let us answer questions about the specific observables in a faster manner. So if I wanted to know what a specific sender address has been up to for several months, I could table scan our main table. That's querying a large amount of data. If we can query against something that's liquid clustered for the use case, it's going to be significantly faster. First, because just liquid clustering is going to help you with file skipping. But also in the secondary tables, they have fewer columns. So ultimately, there's just fewer Parquet files in S3. So we're just going to spend less time loading Parquet footers. Like there's all sorts of secondary speedups. Critically, our main table is liquid clustered by email ID and by message timestamp. And we have those two pieces of information in all of the secondary tables. So instead of loading the secondary tables up with unrelated columns, like if we need something, we want to join back to the main table where the data actually lives. Here's an example of what a secondary table query looks like. In this table, we've liquid clustered by message timestamp, as well as both the reversed sender and reversed recipient domains. So we can quickly look at what a sender or recipient has done, as well as records like specifically between those two. So the basic, like, tell me when and how often query for this takes a few seconds to run on the secondary table. It would take several minutes to do this on the main table. This table can also answer some questions like, tell me all the sender addresses from this domain, or tell me all the domains which have been emailed by this sender. So like these things, from this one table, we can answer a variety of potentially interesting questions. So like we have our fast secondary table, we have our main table with all our information. Here's a join between the two. Like this query must work great, right? I want to know the subjects from the email sent by a specific sender. So we use that secondary table to filter down to just the records we care about, grab that from the main table. Like what could go wrong? If you run that query, it's going to be a catastrophe. This is where the forward-looking statement comes in, right? So at the time of right now of this talk, if you run that query, what you're going to see is it's going to do a full table scan against our large table, and then it's going to do a join against the secondary table, and we've defeated the entire purpose. If you make this change, however, if you just give it a little join hint, all of a sudden we're going to start triggering adaptive query execution, and file skipping is going to just dominate this query, especially if it's a very selective query in the CTE. We go from like a multi-minute query down to like sub 10 seconds. This behavior could change in the future. In fact, I really hope it does change in the future, because if you don't remember to do this, it's a bad day for you. So if you are doing stuff with liquid clustering, always test your queries and look for those file skipping statistics, because that's going to tell you if it's actually doing what you think it's doing. So we've got a set of tables with our data. We can answer a variety of generic questions from those tables, like how do we actually use this to go after that list bombing attack I told you about. So thinking back to the attack, there's a few attributes in the attack that the attacker cannot control. So they have to be sending a high volume, and they have to be sending from a number of different automated systems. If they don't do either of these things, it kind of defeats the purpose of the attack. If you recall from some of those subject lines where they had gibberish names, like if a web form takes a name as well as an email address, we saw the attackers just put random data into this field. But the attacker does control this, right? The attacker could choose to put the actual user's name in there. So we don't want to be crafting a detection around something the attacker can control. And since this is an attack that's targeting specific recipients, we want to build the detection logic around per recipient stats. So what we want to do is take 15-minute time windows and look for users who are receiving large numbers of emails from unique domains, something like 45 different unique domains in a time period. We want to filter out recipients who historically get high volumes of emails from unique domains at once. We're going to do this by calculating the 90th percentile value of that number across that user's telemetry. And basically, if that value is greater than 10 domains, we're going to assume it's some sort of inbox which just gets a lot of contact from all over the place. Like it could be a support or like help desk email address that just gets a lot of churn. Finally, we want to check if most of these emails coming to the recipient during the time window are actually from email addresses which have never emailed them before. And so this logic can be produced entirely from that sender-recipient secondary table. But deciding where to draw the lines is somewhat arbitrary, and so that was something that needed to go through several rounds of tweaks to get it right. So now that we know the attributes of the attack and kind of the critical statistics we need for this detection, we're in a much better place to build some gold aggregate tables to answer the specific questions. So during the prototyping phase, we just need to know, like, can we answer this question at all? But to transition this to a near real-time detector, we need to build a system that lets us answer this question: what users is this happening to right now? Or like right now in telemetry. To do that, we're going to need an aggregate table that is built around that 15-minute window, but we're also going to need some sort of lifetime statistic of just any address that's ever emailed any of our users and the timestamp of the first time that interaction happened. So these gold tables are going to be produced through their own scheduled workflows. For the lifetime aggregate, it's pretty easy to just use a merge into syntax if you've ever used that in SQL. We're only updating a few columns most of the time. For the 15-minute aggregation table, we don't actually do this as a streaming job. We're just going to calculate these blocks twice per hour, but we still want basically real time in our telemetry, so we actually merge a view in, which calculates the most recent block directly from the raw table, and that way we can query the real-time data and use the older statistics to make sure it's performant, but we have the most recent data in that basically a single view. So we've covered how to set up the pipelines to detect this attack in our telemetry, but for me, a big question in my workflows is always how do we take what we now know and how do we actually do something about it? And the point of the talk up to now has been how do we design data tables that let you quickly answer questions that are novel? This is the big benefit for Databricks, if you've heard in any Databricks talk ever. But we want to spare some thought to the idea that if it's easy to build new detections, but it's hard to ship that detection, over time you're going to get bogged down implementing all of the extra bits needed to ship the data instead of focusing on identifying and answering the novel questions, right? If you have domain experts and they spend their time working the data, their time is best served using their knowledge to get more out of that data. We don't want them to have to learn Kafka or learn all sorts of things that might not be related to what they want to be working on. So to try to accomplish this is something newer we're trying, but the pattern we've been playing here is to use a delta table as a single interaction point for an external service. In our case, for email, we have the ability to send a retrospective verdict for a given email. So this is something by email ID. It lets us update the verdict of that after the fact. To do this, it requires sending a specific protobuf with the correct information down through Kafka to an external service outside of Databricks. For the list bombing attack, we could have our single workflow output its results to Kafka. But in a world where we have many different workflows looking for different things, it's going to get hard to manage who exactly is talking to this service. And if something needs to be changed in how we do that, we'd have to roll it out to a lot of places. So instead, we want to split the responsibility into two. We want a Databricks workflow, which identifies the things it wants to send a retrospective for. In this case, this is a list bombing workflow that we've been talking about. And then we want a second workflow, which is going to ship that data to the right location in the right format. This is the logical flow for how we want a research idea to integrate into the external service. On the front half, we have basically the researcher domain. So they're creating new ideas, they're working the data, they're automating their detections, tweaking it. The final result of that is that they're going to have a job which is inserting rows into this table and says, these are the things we want to take action on. From the researcher's perspective, once they get to this point, their job is done, they can go start working on the next thing. And from this point, which is step 3 here, we want to transition this to an export job, which is responsible for validating all the records inserted into this table. And here we can run things like standard safety checks to verify, do we actually want to take some sort of external action? And then we can do all the things like package it up and ship it to S3, or ship it to Kafka, or make some external API call. So by doing this, we can plug multiple research ideas into this one table to ship the results, while still having a single place to monitor the system behavior. For me, super critically, this job gives us a single choke point where we can implement safety checks and guarantee various research systems do in fact pass through these safety checks. And so this is the flow for us. Databricks as a platform gives us the ability to pull in data and answer questions very quickly. So our goal is to be able to run ideas to ground, to prove them out, try to get them running and producing value in the real world. And it's not a shocker, but you want to start with the data that can answer a variety of questions fairly quickly. Don't bother building that single purpose table until you know what that purpose is. For us in threat research, the value is the novel idea. So taking the data and doing something new with it. The more time you're going to spend on data engineering, the less time you're going to spend being a domain expert. On the other hand, like I have this personal hobby called sleeping at night, and a big part of that is like trusting the systems you build to not blow up at 2 a.m. And so first off, this is the value proposition for Databricks and your cloud provider, like you're not managing your infrastructure. But it's also in the designs you choose, like making sure any critical system calls go through these like choke points, and you can make sure you have some control over how these systems interact. And so thank you. Again, a reminder, please complete your surveys, and we have just a couple minutes if anyone has any questions. We have a microphone in the back.